Hey everyone. So today we are going to talk about ML applied to cybersecurity. And cyber attacks usually involve some form of theft. There can be a theft of money, there can be theft of data. It can involve some kind of block of services, or it can involve some kind of like ransom, like you do the thing they want to do and you'll have to pay it, otherwise you'll suffer the consequences. Post COVID and post the digital boom, there have been lots of more devices which are connected to internet. And there are many different kinds of users who may not have the ability to protect themselves. A cyber attacker usually would want to stay undetected because as long as they are undetected, they can do what they want to do. As soon as you find that you're under attack, you take the steps needed to stop that thing. So I have titled this talk Sherlocking the Clues of an Attacker because whenever someone is trying to evade detection, they would leave a trail of clues. And those clues are very good for a model prediction because there is an anomaly behind them. And that's not how normal data should look like. During my past 1 year of working at Elpha Secure, where we try to raise alerts on some of these anomalous behavior, I have had the chance to study how cybersecurity tries to tackle this problem traditionally and how ML can come in and help in here. So, clues can give away attack activity. However much someone is trying to avoid being detected, they would still leave some patterns. But relying on a single clue can be dangerous because you could be raising alerts when there shouldn't have been an alert in the first place, and that could lower the trustworthiness of your models. But you would still want to have a fleet of sensors and models which are sensing all this activity to reliably deliver alerts. One of the problems which happens in cybersecurity is zero-day attack. A zero-day attack would usually involve some form of vulnerability, which was discovered very recently, and threat analysts haven't had the time to dissect that problem. You wouldn't know what usually happens in those kind of attacks, and if it's a team of humans looking at it, you may or may not be able to catch it. So, one of the broad goals of ML at cybersecurity is to be able to detect attacks which have not been seen before. And you would want to gather as many clues to come to a decision quickly. There's an element of time because more and more time the attack has gone undetected, the harm would have occurred. And I feel that cybersecurity is a very interesting area to apply ML. It's a game of cat and mouse. The attacker is always trying to avoid detection. What could have worked with 90% of accuracy before may not even work with 60% of accuracy tomorrow. There is a lot of data, which is good for us ML practitioners. Systems generate a lot of data for logins, for command logs, for process creation and all. And there are clues in that huge bundle. There is also an element of satisfaction because if you're able to stop a malware before it executes, you're actually protecting someone from a loss or a potential damage. Oops. So, how do we begin modeling for this scenario? There's this security aspect of it, which is called MITRE ATT&CK framework. MITRE is a not-for-profit public organization which is involved in threat analysis and how past incidents have occurred. And they have put up this framework, a chart, which lists down commonly used adversarial tactics and techniques. If you want to model how a cyber attack is going to happen, you can use this framework as a prioritization tool to look at the areas where you want to stop. Now, this chart is very big. You would see that there are many titles, initial access, execution, and persistence. How do you learn to read this chart? One key takeaway when you are trying to learn to read this chart is this chart goes from left to right direction. What I mean by that, usually whenever an attack happens, the attacker would do the steps on the left first, and then they would try to move on to a right direction. There's a chronology from left to right. So, reconnaissance, it basically means that someone would try to gather more information about the user, which organization they are working with, what kind of capabilities they have. Resource development, once the attacker has learned what the victim is or where they are working, they'll try to develop the resources for them. Let's say they want to launch a botnet attack. What kind of infra do they need to build on their own side? Initial access. Initial access would mean how do you get first approached by this attacker? It could be something as simple as a drive-by compromise where you actually are browsing a page and that page has some malicious ad or some kind of iframe which drops the malicious payload. Or you could have been a victim of phishing. Phishing involves sending you a link which directs you to some page where you could have like some payload downloaded to your system. Many a times there is an aspect of social engineering involved in phishing, and that means there is an aspect of NLP also you can use to solve that problem. Execution. Execution means what this attacker needs to do in order to actually launch their attack. It could be involving some kind of command, some kind of bash script they need to run on your system. Or the attacker could try to use some form of inter-process communication to go undetected, like use some form of Windows DLL to launch their malicious attack. We basically use this framework as a guide rail. An attack would have multiple things going wrong. It won't be a single thing. You don't want to be crying wolf all the time. I guess all of us in ML agree that false positives are bad. But I think in our case, it's even more important because if you have shown them too many alerts in the past 1 week, maybe the user won't take you seriously. And that would defeat the whole purpose of your job. So you'd want to use this framework as a guide rail on different aspects. When do you see that some access has been taken away? When do you see some form of abnormal command is happening? Or when do you see some form of abnormal process running? You would want to use the prediction on 2 or more of these items as a checklist to raise an alarm with confidence. And what this talk is about. So there are some security aspects which I cannot talk as like we are actively shipping this product, but I'll still try to list out what are the possible clues which show up as an anomaly and how each of these anomalies can be used and translated to an ML modeling problem. Each of these anomalies can be seen as a feature, as an input sample. And once you have those input features, you can like choose your own choice of model. Some of the anomalies which I want to talk about are command entropy, file entropy or file histogram, and process trees. So I have had the experience of working with anomaly-based models a lot in this field. And I think cybersecurity does use it a lot. Many a times you cannot rely on having labeled data. You cannot be thinking that you will always have a case of that particular anomaly happening before. You couldn't be too dependent on supervised learning. An anomaly-based model fits in very nicely here because it knows what is normal versus what is abnormal. At training time, maybe it has only seen cases of normal data. It has learned their distribution. And at test time, when a new data point comes in, it will try to judge if that test sample is an in-group or it's most likely to be an outlier. You would want to feed your input features to each of these models. Isolation forest is pretty useful in this case, but there are others also like one-class SVM or local outlier models. First clue. If you look at your command logs, there would have been one abnormal command. Usually a non-harmful command like the one at the top. You see something like a smart screen launched at system 32. Now it has no reason to be undetected because it has nothing to hide. But if you look at the command below, it's a stealth command. It's gibberish. It doesn't make any sense. And there's a high probability that someone is trying to like run a command which could have a very bad impact on your system. The probability of this command existing is very low. And this should raise suspicion. This is a strong red flag. And this is actually a very easy ML problem. It's really an easy ML problem because the basic principle at work is just that the probability of the next item given the present item. We all know Hangman. We all play Wordle. We know like basically when we have seen those kind of examples before, what is the missing item there and what is the probability of each of those items. Any of the obfuscated text, any of the encrypted text won't fit any of these usual probabilities. And that's a very strong hint. So If you have a corpus of all these commands, this is in principle a language model where you learn to predict the probability of the next token given the previous token. So in that image, we see basically what your normal commands would look like, and that's from my system only, I think. You would have some wgets, you would have some tmux, you would have some bash. But you would never see an instance of some command which is very obfuscated. And if you have trained a model on this kind of corpus, it would be very easy to detect when something is belonging or not belonging to the training distribution. Another clue, file histogram. A file histogram basically opens a file, looks at the byte symbols, which go from 0 to 256, and then it tries to plot their frequency. So on the left side, if you see a normal.tif file, you'd see it has a very skewed distribution. Some symbols are very represented, like 250. Some symbols are totally missing in this. On your right, it's an encrypted.tif file. And encryption usually smoothens the byte entropy distribution. There's more randomness involved. An actual TIF file may have some file format, like the header should have this image description, or the file ending should be describing some color property. But once someone has tampered with that file, it would lose all that distribution and the structure, and it would look something more random, more entropy. Same case for a .png file. Again, on your left, you see a very skewed distribution with some huge spikes near 50 and 150 and 250. Whereas for the same file, when it has been encrypted, it shows a more smoothed out distribution. And this behavior can be seen across all different kinds of encryption. That's a very good hint. So an actual file is basically like a sequence of bytes. There is some conditional probability involved, which makes sense. So let's say the probability of a 00 symbol followed by a 00 symbol is very high. But the probability of a 01 symbol happening after E2 is impossible. Encryption breaks these probabilities, and we know that the probability of any gibberish is going to be very low. So we could read a file, look at its byte histogram, or learn the conditional probability of the tokens, and be able to predict when something is an anomaly or not. Another anomaly which can be used is process tree. So a process usually has a parent, and it could have a child process. There would be a normal chain. So like in this figure, there is 0, which could be thought of as the root, and the root is launching different processes. Let's say it's launching some SSH process, it's launching some tmux process, or it's launching bash. And then bash on its own is also launching something, some kube control command, or some Perl script. If you have lots of process logs, you would know like what kind of chain of execution is very normal, what kind of parent and child processes usually happen after each other. What can happen is, if an attacker has got into your system, they would want to launch a process which is very abnormal. So you would usually launch Microsoft Word from your system. But if you ever see like Zoom has been launched from Microsoft Word, there is no reason for that thing to exist. And that's a very big anomaly. So how do we develop on this clue? You can learn the edge probability between the parent and child processes. If you look at the edge connections, there are some weight terms. And these weight terms can be as simple as the frequency of times those connections have occurred. You can make a probabilistic model for each of those edges. Either you can learn to have an edge prediction problem, or you can make a whole graph out of it. You can also involve NLP, because many a times the process names can slightly differ over time for different versions. You can learn to embed the process names. You can even embed the process names along with the user path, because sometimes there can be a case where someone has spoofed a process name. So even though it shows up as a daemon process, the path would be something else, and that's an anomaly. So you could learn to embed the process names along with the path, and then treat them as a sentence, as you do in NLP, and try to predict if this combination of edge probability and this combination of process embedding has occurred before or not. Another clue you can use is suspicious logins. As soon as you lose your credentials, what do you think is going to happen first? First thing they are going to try to do is to log into your system, because only then they can do like what they wanted to do. Your login as a user would follow some patterns. Maybe you wake up at 9 a.m. and you log into your system at 9:15 a.m. You take a lunch break at 1 and maybe log off work at 5 p.m. Your login is going to follow a regular pattern of your time, your day, your hour, and your location. You can easily make a feature out of this, and you can then feed those features to a model which can know when something has followed usual distribution and when it's an out of group anomaly. And you can run alerts on each one of them. Each of the anomalies I talked about may not be a foolproof alert on their own, but if there is a combination of all of them, following a pattern of going from initial access to execution to an actual command run, you should be able to know whether you are actually under attack or not. And ML and data is our friend in cybersecurity. Traditional security involved lots of human security analysts sitting and trying to find out patterns, but that was not scalable, as that would involve excess of code for each particular situation. There would be scalability challenges when newer threats come up. But ML is very good at observing patterns, and that's why it's a very good friend in this field. Last thing which I want to talk about is, I think, the usual challenges in deployment. As usual, there can be features which you have trained, but the features have drifted over time, and they don't occur in your test distribution. You need to monitor with any of the choice of tools which you use so that you are able to retrain your model with time. You should also be looking at the ratio of alert predictions, because it could be that something has changed internally. Maybe your data, which you were expecting in a certain format, has changed, and then you suddenly see a spike of alert predictions compared to the safe predictions. And then you should step in and do some troubleshooting. And then there's always a trade-off with false positive alerts. You want to be safe. You want to be very sure when you're raising alerts, but you don't want to be a hyperactive alerting model, because then you would end up being uninstalled. So yeah, these are some of the things which come up during deployment time. And I think that's it for me.